All right, today we're going to take a look at friction. I encourage you to have your data page ready because we're going to be recording some data as usual. Your friction handout looks like this. And basically we're going to be trying to measure the coefficient of friction, mu, remember that's the Greek letter mu, kinetic friction, static friction, both of these by watching something actually sliding on a board. The idea is this. We're going to take a block of wood, connect it to a string that passes over a pulley. We're going to place some masses on a hanger so that the block of wood is moving at a constant speed. What this tells us, if the block is moving at a constant speed, it tells us that the tension in the string must be equal to the force of friction, in this case kinetic friction. If those two forces are equal, then the block will be moving at a constant speed with no acceleration. So the tension is created by the weight of these masses. So the weight of these masses effectively equals the kinetic friction, because that's what's causing the block to move at a constant speed. Now we're not actually going to be using forces here, we're going to be using the masses. We know that mass isn't really a force. mg is the weight, which is a force. But in the equation, the two forces will cancel out the g, so we're just going to pretend, as we did before, that the grams are a force. Okay, so the setup looks like this. We've got a block of wood attached to a string, passing over a pulley from which a 50-gram mass hanger is attached. Now let's just take a look at the procedure here and follow the procedure just like you would if you were in the lab. It says weigh the wood block and record its mass on the data page. So we're going to have to, I'm just going to grab the balance, bring it over here. All right, so we've got the balance here. We're going to find the mass of the block of wood. I'm not going to worry about the weight of the string. And we can see what this block of wood actually weighs. Actually, it's the mass we're determining, not the weight. Too much. So there's 200. Too much. A little bit too much. That's 250. And whatever single grams it takes. Okay, that's about right. So we have 257.5, 257.5 grams. Now we're going to write that number on the data page, right here where it says mass of the wood block, 257.5 grams, plus or minus, let's say 0.05 grams. So we can put a 0 here. Okay, so taking a look at the procedure, lay the board with the pulley on one end on the table, with the pulley end overhanging the edge of the table, place the wood block at the other end, and the string to the hook in the block running over the pulley. Okay, so we're going to run the string over the pulley with a mass hanger hanging from it. Okay, so this is actually a 50-gram mass hanger. It says give the wood block a slight push. Okay, notice the block isn't sliding yet because static friction is stronger than kinetic friction. So that's why we have to give it a little push to break the static friction to see if there's kinetic friction is small enough to let it slide, but it's not. So because it's not sliding, it says If the block isn't sliding, you should add masses, add a few grams of mass to the hanger. This is a kind of a tricky part here. I'm going to start with, we don't really know exactly what it's going to take to let this thing slide at a constant speed. We have 50 plus another 50. It's probably too much. Notice it's accelerating. It's going way too fast. We have to find just the amount of mass that causes it to slide at a constant speed. So here I have a 10 gram added to the 50. So that's going to be 60 grams. Now if I give it a little bit of a push, still isn't moving. Let me try adding another 10 grams to it. Almost. You can see it's trying to move. Let's try another 10 grams. It might be too much. Getting very close. Now we know 50 was too much, so let's try another 5. That'll bring us to 85. Oh, look at that. Okay, beautiful. Okay, so now we have 85 grams there, and it looks like if I give it a little push, it moves about a constant speed. Accelerating a little bit, but it kind of depends on where it is on the wood. So what this tells me is that this hanging mass is equal to the force of friction because it's going at a constant speed. So what we want to do, if you look at your data page, you'll see for mass placed on the block, we haven't placed any extra masses on the block yet, so that's 0. The total normal force. Okay, the normal force, remember, we've got the weight of the block, we've got the normal force. Normal force is just the force that's squeezing. You see, that's what it is with friction. With friction, the stronger you squeeze them together, the greater the friction. So that's why the normal force is important. In this case, we're just going to call the normal force the mass of the block. And the mass of the block then is just the mass of the wood block that we've already measured, 257.5 grams. Now, force to keep the block moving. What's keeping the block moving when I push it is the hanging masses. So let's be careful and count these to make sure we've got it right. We have 50 for the hanger, 3 10s, that's 80, and 5, that's 85 grams. So force to keep the block moving uniformly, 85 grams. Okay, now, if we increase the normal force, what's going to happen? You know that the friction will increase, right? Because the friction, the formula for friction is just kinetic friction, UK, times the normal force. So if we increase the normal force, it should take a greater force to get the block moving at a constant speed. So how do we increase the normal force? We're going to add 200 grams to the top of it. Okay, so I have a 200 gram mass here. I'm going to place it on the block. And we're going to do the process again to see how much mass it'll take so the block will slide at a constant speed. Last time it took about 85 grams, so I'm going to guess it's going to be over 100. We have 50 in the hanger. I'm going to place another 50 here, and I'm going to give the block a little bit of a push. And you can see it's not enough to make it slide. So let's take a 20. Put it on there. Here's a 20. So that's 120. Well, we've got 200 grams on here now, so the normal force is greater, so the friction is greater, so it takes more mass to get it to slide. Getting close. Let me put another 10 grams on there. Need a little bit more, another 10 grams. Oh, there we go. You see that? That's moving really slowly, but at a constant speed. That's perfect. Beautiful. Okay, so on your data page, we have 200 grams on top of the block plus the mass of the block. So that's 257 plus 200. That's 457.5 grams. And the mass that keeps it moving is the hanging mass, which in this case is the 50-gram hanger, plus an extra 50 grams, plus 20, that's 70, 80, 90 grams of mass. Oh, that can't be right. 50 plus 100, that's 100, 120. Gotta be sure to get this right. Okay, so this is 100. Yeah, that's 50, 50, 120, 30, 40, 50, 60, 170. Whenever you make a mistake in writing your data, just cross it out with one clean line and write the new data point. So it took 170 grams to get the block moving with 200 grams on it. So now let's put another 200 grams on there to make 400 grams. You see what's happened. $200 plus 200, that's 400 grams. It should take quite a bit more mass now to get this thing to slide at a constant speed. Last time it took 170, so let's guess it's going to take 200. So I'm going to take, let's see if I can find 100 grams here. Yeah, so we have 150. I'm going to put another 50 on there to make it 200. And I'm guessing that won't be enough to make it slide at a constant speed. Oh, almost. Let's try putting another 10 grams on there. Very close. Oh, that looks good. See, it kept going. It's a little different on different parts of the wood because the wood characteristics vary from place to place, but along a certain portion, it's pretty constant. Oh, that's nice. Okay, so now we have 400 grams on the block plus the 257 of its block's mass. That's going to be 657.5. And the mass that keeps it moving, we saw was 50 plus 100, that's 150, 200, 210 grams. So we're going to write 210. You see the trend here. As the normal force increases because of the weight on the block, the force to keep the block moving is also increasing. Let's do a couple more. Next we're going to try 600 grams. So we need another 200 grams. I'm just going to reach over here to this other box to grab that extra 200 grams. Here we go. So now we have 600 grams on the block. What's it going to take to get it to move? Well, for 400 it took 210. So I'm going to guess it's at least 250. So we have 100 plus 50. 50 plus 50 is 100. 200. And let's try 250 and see what that does for us. Okay, put these masses back on. Okay, let's give it a little push. See if it goes. Almost. Let's try another 10. Notice if the mass is swinging, that could cause the tension in the string to vary a little bit. That might be a source of measurement error. Still not quite enough. Let's add another 20. See what that does. Okay, that looks pretty nice. Slow is good as long as it's constant. It's pretty good. It's a little bit jerky because of the irregularities in the wood. I'm going to try another 10 just to be sure. Might be too much. That looks good. Okay. So now we have 600 grams plus the 257 rather. That's going to be 857.5. And the masses that are pulling on the block, we have 50. 50 is 100, 200, 250, 270, 80, and 90. So 290 grams. All right, next is 800. So I've got to get another couple of these big masses here. Okay, now this one is 500, so I'm just going to put 500 here. And what we need is 800, 500 plus 200, 700, and 100 is 800 grams. All right, let's see how much more mass it takes to move that. Last time it took 290. I'm going to guess we're going to need like 350, so let's just try that. 50 plus 50 is 100. Plus 200 is 300. And let's put 50 grams on there, so it's 350. Wow, that's just about right. Maybe another 10 grams. There we go. Look how smooth and constant that is. So we had 360 grams hanging from there. So I'll write that in here, that's 360. The force to keep the block moving, we have 800 grams on top of the 255 block, so that's going to be 1,057.5 grams. We've got one more to go. That's 1,000 grams. We have 800 here. Put another 200. Now I've got 1,000 grams. I'm going to distribute that a little bit more evenly. Got 1,000 grams on that. And let's see how much more mass it takes to get that to move. What we had before, we had 360. Let's take off the 10 to make it an even 350. I'll put another 50 on it, so that's 400 grams. Not enough. Let's try an extra 20. $420. And that looks real good. Okay, so now it took 420 grams to get 1,000 plus 257, 1257.5. Now, what we have here is a set of data which are increasing together. So what do you think we're going to do with this? According to the calculation page, obviously we're going to draw a graph of this. Calculation page here. Calculations. Using the data from procedures 1 through 5, which is what we just did, plot a graph of the kinetic friction force versus the normal force. Okay, so this is going to be a graph. Kinetic friction force versus the normal force. Now in our data, the kinetic friction force is the numbers we were just writing. The force to keep the block moving. Now that was the hanging mass there. So how can we say the hanging mass is equal to the friction force? Because that's the mass, that's the force that was keeping it moving at a constant speed. So this is labeled Fk. So that's your y-axis on the graph. And the normal force is the x-axis. And hopefully when you plot these, it'll be fairly linear. Now, according to the calculations, calculate the slope of the line. Now, I gave you a PowerPoint last week to explain how best to find the slope of a line. And remember, what you need to do is take a straight edge, draw the best straight line through the points. It doesn't have to touch any of the points, but it has to go like through the middle of the points. Once you've done that, choose two new points on the line and use those points to find your delta y and delta x. And the slope will be your delta y over delta x. In this case, it's going to be friction divided by the normal force. But look, our formula for friction is mu times the normal. So what is friction over the normal force going to give us? Fk over n is going to give us the coefficient of kinetic friction. So once you calculate the slope of this graph, you'll have mu sub k, the coefficient of kinetic friction. Okay, so the next procedure asks the question, what if we turn the block on its side? Would that change the friction at all? Would the friction be different? Some of you are probably thinking, well, there's less surface area in contact, so wouldn't there be less friction? But on the other hand, you have the full weight of the block on a smaller area to increase the pressure. Wouldn't that increase the friction? It turns out that both of those answers are yes. Since the friction, the area decreases, but the pressure increases, those two forces exactly cancel out. So counterintuitively, it turns out we would expect the friction to be the same. Now to check to see if it's really the same, we go to procedure number 6 here. We're going to place the block on its side, on its edge here, and we're going to place 400 grams on it. Now notice that if I put this on its side, the string is no longer exactly horizontal because the hook is up here. To make this string be horizontal, I'm going to reposition this little hook down here, a little bit lower, so the string won't be at such an angle. Now the string is pretty horizontal. I'm going to put 400 grams on there. Now notice we've already had 400 grams on the block, and this is how much weight it took to get it moving at a constant speed. So we're going to repeat this experiment just on its side with just the 400 grams and compare and see how it looks compared to that. So what did it take before? It took 210 grams of hanging mass to get it moving. So we have 50 plus 50 plus 100. Start with just 200 grams. All right. Looks pretty close. How about that? It looks like that's just enough to make it move at a constant speed. It's still going. So that's just about perfect. So on our data page where it says block sitting on its edge, 400 grams placed on the block, plus the 257 to make 657.5 total normal force. And the force to keep the block moving, we said was, what did I say, 200? Yeah, 200 grams. Okay, now what we can do, we can calculate that's what your next calculation says to do. We can calculate mu from this. We can calculate the coefficient of friction from this, because all we need for that is Fk over N. Here we have Fk and N. So if we just divide the Fk over the normal force, we can get the coefficient of friction. Now using this data up here, we got the coefficient of friction by drawing a graph of many data points. The advantage of that is that we can cancel out the experimental errors by drawing the best fit through those points. But for the sake of just comparing on side to flat, we're just going to calculate mu by going Fk over N and compare that with the slope that we got from the graph. This is all written down in the instructions for the calculations. Find the calculations, here we go. So, calculation 1, we calculated the coefficient of kinetic friction from the graph. Calculation 2, using the procedure from data 6, which we just did, calculate the coefficient of friction just by Fk over N. And then it says, calculate the percent difference between those two. So we're going to have mu calculated from the slope of this graph. We're going to have mu calculated from this single data point, 400 grams on its side. And it says calculate the percent difference between those two. It should be pretty close, but with friction, things get a little weird sometimes. And because of the irregularities in the materials, sometimes you get a fairly large percent error. If you get 10 or 15 or 20%, don't be too concerned about it. You get 1,000%, go back and do it over again. Okay, so what's next? All right, we got up to procedure 6. All right, we've done the coefficient of kinetic friction. How do we do the coefficient of static friction? That's procedure 7. For coefficient of static friction, what we're going to do is just what we did before. We're going to lay the block flat on its side. I'm going to reposition the string again. And we're going to place 400 grams on it. Two plus 2, 400 grams. All right, we're on procedure 7. Put 400 grams on top. Repeat step 3. That is adding masses to get it to move at constant speed. But this time, do not push the block. Just keep adding the masses to the hanger until the block moves on its own. Now we're talking static friction. Because by not pushing the block is not moving, it's static. And we'll see how much it takes to get it to move now, it's not going to move at a constant speed because once it breaks free, the friction is less, so it's going to accelerate. But just the exact amount that causes it to break free, that'll tell us the static friction force. What do you think? Is it going to be more or less? Here we had 400 grams with kinetic friction. It took 210 grams to get it moving, sliding at a constant speed. What do you think? Will it be bigger or smaller value this time to get it moving? Well, because static friction is generally greater than kinetic friction, we're going to expect that it's going to be bigger. We have 50 grams there. Put another 50 grams on. Last time it took 210 grams, so I'm going to put another 100 grams on there, so that's 200. I'm going to put it on carefully so I don't jerk it. If I jerk it, it breaks the static friction, but I want to maintain the static friction. And gently put the mass on to see if it breaks. Oh, it's too much. Interesting. Interesting. That's because I put 200 grams on there when I was thinking I was putting 100 grams. It's not a problem. So just do that once more. That's why it broke free, of course. I'm going to have 50 plus 50 plus this time 100 grams. I'm not expecting it to break free with just 200 grams. Okay. Block is sitting there, not moving. It's static. 200 grams is not moving it. Let's try 210. Still not moving. Let's try another 10 to make 220. Still not moving. I'm getting a little impatient. Let me add 20 grams and see what happens. Whoa, too much. Okay, so let's go back and take the 20 off. Try it with 10. Okay. So let me try it with just 10. Nothing. I'm going to just put 5 on now, because I think I'm getting close. Oh, it's moving. Okay. So apparently, the mass that's hanging here was just enough to overcome the static friction with 400 grams on it. So let's see how much we have here. We've got 50. Plus 50 is 100. Plus 100 is 200. 210, 220, 230. Well, it was not much more. Not much more than it was before. Oh, thank you. So now on our data page, we have block laid flat, block to start block moving uniformly. That's Fs, static friction. What did I say? 240? 240 grams. And the total normal force was 657.5 as before. This will allow us to calculate the coefficient of static friction. In your lab report, you'll want to talk about how mu static is greater than mu kinetic, because static friction in general is greater than. Why is static friction greater than kinetic friction? If you look at a microscopic image of two surfaces, like a tabletop and a block Friction is caused by the roughness between the two surfaces. And as long as it's sliding, it's like sort of like hydroplaning. The blocks are passing over each other quickly, but as soon as you stop and let the block settle, the bottom of the block, the little hills and valleys in the bottom of the block settle in to the bumps of the table. And that kind of locks it in place, which is why it takes a force to unlock the static friction so that it can slide with kinetic friction. Okay, we're not quite finished yet. We still have another way to calculate the coefficient of static friction, and that is procedure 8, which is to raise the end of the board slightly so it rests on a horizontal rod and remove the string. Okay, what we're going to do is, let me just tell you what we're going to do. Okay, we're going to take this string off the block. We're just going to lay the block on the board. Just remove the string here completely. With the 400 grams, keep everything the same as it was before. Only this time, we're going to find the coefficient of friction by raising the end of the wood until the block slides of its own accord. It's got static friction right now. To break that static friction, it takes a certain angle. Now, before we actually do it, let me show you the math behind this. What we have is the board, table. Draw this a little bit better. That's not good. And the block. Now, what's the force pulling the block down the inclined plane? We know there's the weight of the block, which is mg, and the weight of the block has components. We've seen this before. We have a perpendicular component, and we have a parallel component. And if this is the angle theta between the wood and the table, then that's this angle here, theta. So this component of the mg force, since opposite over hypotenuse is the sine, this is going to be our mg sine theta force. Now, that's the force that's going to break the static friction. Since F static equals mu static times n, F static is just going to be mg sine theta. But what's the normal force? The normal force is the perpendicular component, since we have adjacent over hypotenuse. That's going to be mg cosine theta. So the normal force is just mg cosine theta. So a wonderful thing happens here. First of all, the mg's cancel out, being both sides of the equation. If you solve for mu sub s, take the cosine under the sine. What's sine divided by cosine? Is just the tangent of theta. So it's very nice. All we have to do is measure the angle at which the block breaks free, take the tangent of that angle, and that'll give us the coefficient of static friction. We already measured the coefficient of static friction one way. This will give us another way to get it, and we can compare with percent difference. Now, measuring that angle is a little bit tricky. We have to be really careful. This is diagrammed in your lab handout. How do we measure that angle? Well, what we're going to do is choose some spot on this board. We're going to use the bottom of that because that's what touches the table. And we're going to measure this distance here. And let me make sure that I'm using the same terminology as your handout. we are. We're going to call this y. We're going to measure the distance from where it touches the table to that point. We're going to call that x. We're going to measure y and x and record that on your data page as x and y. From that we can calculate the angle. The angle is just going to be the inverse tangent of y over x. And then we can write the angle here. So let's do it. Let's see if this actually works. First I'm going to turn the board around so that I don't have to worry about this pulley. This is a little tricky. Usually you're working in a team and one person can be doing this and the other person can be doing that. But I'm going to give it a try anyway. Here we go. Got the block with 400 grams on it. And the deal here is that as soon as the block breaks free, I'm going to freeze the position of the board by putting it on this rod here. So, it's a little tricky to do by myself, but I'm going to give it a try. I'm raising it very, very slowly, until we reach the exact point where the block breaks free. We've got a problem. That frequently happens with lab activities. I've got my masses sliding before the block. So I'm going to just put a piece of tape there. Keep that from sliding. That's one of the reasons we do labs, is to see what kind of problems accumulate. This is kind of a crude fix, but should do the job. All right, let's start over again. Okay, I think I'll just keep this under here and raise it with the rod. All right, here we go. Gonna let that set there. Sometimes the static friction increases over time because there's more time for the little bumps to settle in to each other from the top and the bottom. Okay, I'm gonna very slowly increase the angle. And as soon as it begins sliding, I'll stop. Okay, there it goes. I'm going to lock the position in here. And now we can take our measurements. Okay, we've got the angle here. So now what we're going to do is actually measure x and y. It doesn't really matter what part of the board we use to start with, because the angle is going to be the same everywhere. So I'm just going to put a little piece of tape here, put a little mark right here, and then directly below that. There are a lot of ways to do this. You might be able to come up with your own way if you're doing this in the lab. Right beneath that, place another little mark. So right off the bat, we can measure y. It's just this leg of the triangle. You see the triangle there? So that's going to be from the bottom of the board. It's going to be 20, 25, looks like 25 exactly, 25.0. I'm just going to write that down here. Y is 25.0 centimeters. And x from our point to where it's actually touching the table, the wrong side here. Looks like about, now I'm measuring from where it's touching the table, not the top, from down here. Looks like 95, about 95.2. So for x, I'm writing 95.2. Let's just do that a couple more times. And it'll be interesting to see if it's consistent or not. It probably won't be because that's the way friction is. It's a fairly inconsistent phenomenon because, as I said, the variability of the roughness of the surface. So once again, it's important that I raise it very slowly so as not to jerk it free from its static friction, but it breaks free just because of the mg sine theta force component of its weight. There it goes. Okay, let's see if the measurement is similar. Make sure that this is directly underneath. Moved a little bit, so I'm going to put a new point there. So y is going to be to the bottom 24.5. Pretty close. And x is 95. No, it's about 94.8, I would say. You could see a lot better if you were here in person. So it's pretty close, actually. Better than I expected. Let's do it one more time so we can get a good average. Here we go, very slowly. Wait for it to break free. There it is. Just barely. Let's see if it's still consistent. Okay. Looks like this has moved a little bit again. I want to measure it from directly beneath. Right about there. So it's going to be 23 exactly. So y in this case is 23.0. A little different. And x is about 94.7, I would say. So that angle is going to be a little different because the x is about the same, but the y is a little different. Doesn't matter, we're going to take an average. So then all you need to do is calculate the angle from those two numbers. Remember, y over x is your tan theta. So theta is just inverse tangent of y over x. You can calculate that and put your numbers there. Then, to calculate the coefficient of static friction, we've seen that that's just the tangent of theta. And then you can take the percent difference between that mu s and the mu s we got before by hanging masses while it was static. In your lab report, in your discussion, you want to be sure to talk about the shape of your graph and what it tells you about the variables. The fact that Fs is proportional to n. Discuss the percent differences that you calculate. Be sure to evaluate those and talk about are they acceptable or they're not acceptable. Be a little easy on yourself with this one because, as I said, with friction, sometimes the percent errors are fairly large. Also discuss the fact that we found the coefficient of kinetic friction between the block when it was flat compared to it with it on its side. Talk about whether they should be similar and if they actually were similar or not and why that's the case. Make a complete list of the sources of measurement error that limit the accuracy. There's lots of things here. You know, just raising this is a difficult process to do it without jerking, and there's lots of things that can create measurement error. And then just talk about the overall experience while you're doing the lab. So, if you have any questions about any of this, be sure to email me through the Canvas inbox, and that concludes our lab activity for friction.